example number 2, it says use the graph of 2 to the x. So I'm going to start by graphing 2 to the x, which would have 0, 1, and 1, 2. And one of the reasons that this wasn't done, like we could have added this as a graph in chapter 3 and just had one more paragraph. I gave you the yellow sheet, the green sheet, the pink sheet, and the blue sheet. I could have found a different color paper. Salmon. Could have made a salmon sheet and had exponentials. The problem with exponentials is there's more than one of them. They all look the same, but there's a 2 to the x parent graph, a 3 to the x parent graph, a 4 to the x, a 5 to the x. There's a whole bunch of them. So that's part of the problem. The other part of the problem is because in the parent graph of an exponential, there's a number that's big. Like x cubed had a little 3, x squared had a little 2, but this has a big 2. It causes problems with transformations. Because sometimes when students get to this equation here, they might be like, ooh, 3 beside a 2, 3 times 2 is 6. Careful, order of operations. Your exponents happen before multiplying, but you see the 3 times 2 right next to each other, you're going to be tempted to multiply them too soon. So sometimes what I find helpful is I take out a highlighter and I highlight the 2 and the x, because that's my parent graph, right? My parent graph has a 2 to the x. And if I highlight the 2 and the x, everything that's left is going to be a transformation. So when I look at what's left, I'm like, oh, a 3 outside. Are you okay with that being a vertical stretch? The negative, anything that's in the exponent is going to be horizontal. So this negative in the exponent, that's a horizontal reflection. And this 2 is going to be a horizontal translation. With the vertical stretch, do you multiply by 3 or multiply by 1/3? By 3. Horizontal translation, would that be 2 to the left or 2 to the right? Okay. It's not in factored form. Do you remember that special note? Anytime you have a horizontal reflection and horizontal translation. So they're really starting us off with hey, do you remember everything? So I would rewrite this 3 times 2. I'd factor out that negative. It's going to be 2 to the right, even though it looks like to the left originally. Especially when I write it like this, 3 times 2. Can you see why you're going to be tempted to change that to a 6? Don't do it. You have to do exponents first. And unlike DAB-C, where we had a shortcut for exponential graphs, we don't have any new additional shortcut. We're going to just do it the original way, where you write down your points, and we're also going to write down our asymptote. Do all of our stretches and compressions first, followed by our translations. So here we have x by a -1 and y by a 3. And the only translation is going to be 2 to the right. So we're going to get 0, 3, -1, 6. 2 to the right will give us 2, 3, and 1, 6. And with your asymptote, I often put a longer arrow with the asymptote because the asymptote starts at 0. So no amount of multiplication is ever going to change 0. Because if you multiply anything times 0, you still get 0. With a horizontal asymptote, can you see that moving it left and right keeps it exactly where it was? The only thing that's going to change it if you move it up or down. This one doesn't move up or down at all. It's going to stay at y equals 0. So now we have enough information. We're going to graph this. And I always recommend drawing your new graph separately. Put my arrowheads on there. Put my asymptote down. I'm going to have 1, 6 and 2, 3. And once I have those 2 points, I'm going to be approaching my asymptote this way, get that general shape of your exponential function, and we have our answer. Now to answer the questions they have, is it increasing or decreasing? It happens to be decreasing. Once again, there are no x-intercepts. And unfortunately, I can't see on my graph where the y-intercept is. However, you can always find a y-intercept by plugging in 0 for x. Can you see if you plug in 0, you're going to get 2 to the positive 2 up here? 2 squared is 4 times 3, you're going to get 0, 12. The asymptote equation is still at y equals 0. Domain is everything, and the range is bigger than 0. Now, before I give you homework, I'm going to give you a couple of other examples. Page 357 is a blank page, or maybe you want to do these, maybe there's enough room just in the columns of page 346. Yeah, why don't you start at the top on the side of page 346, and we are going to do a couple more examples, okay? Just right beside, you're on 347, right? And I think on 346 you have a whole column there with nothing written.
You mean we have a space further halfway through?
Yeah, and then
example 1.
Oh, example 1 went. Oh, then you can turn to page 357. 357 is blank if you don't have room on. But here's our first graph. We are going to graph y equals -5 times 3. This one I'll already do in factor form. 2 to the x plus 4. Let's see, -7. So the first thing, if you were given a question like this, that you have to recognize is, what is the parent graph? Y equals something to the x. What's the base of this graph? It's going to be a 3. So once again, if I took out my highlighter, I would highlight my 3 and my x to remind myself that those are not part of any transformation. A little quick sketch of 3dx. Right? As the point 0, 1, and 3 would have 1, 3. So if I take those points, 0, 1, 1, 3, and my asymptote at y equals 0, stretches compressions first, translation second. Okay, the -5, that's going to multiply y by a -5. And anything that's in the exponent, this is your horizontal section right there. So that 2 is going to be x by a half. That plus 4 is going to go 4 to the left and 7 down. Now we just have to do the mental math. We're going to have 0, -5, and 1 half, comma, negative 15. 4 to the left will give me negative 4. And I'm going to change this to a decimal, negative 3.5. And 7 down, negative 12 and negative 22. And for my asymptote, the only thing that's going to affect it is moving up and down. So my asymptote is going to change to y equals negative 7. So now, if I go to graph this, this time, I don't know if I'm going to do the little ticky marks, because I'm going to have to go all the way down. Maybe I'll go. Are you okay with going down by 5s, so you don't have to do quite as many? Our asymptote is at negative 7. I'm going to have a point at negative 4, negative 12, and another point at negative 3.5, negative 22. Smartboard's not liking the brackets. That's so weird. Okay. With those points, it's increasing from here to here, so to go towards the asymptote that way, and down in that direction. And you can do a little bit of, like, the negative in front, that's a vertical reflection. That looks like the vertical reflection happened. You can do a little analysis of all the transformations to feel like, because sometimes you should have a gut feeling that things look bad. Right? Some of you are like, I had that feeling throughout my entire test, almost all the way through. No, that's not necessarily a good thing. Maybe it happens sometimes. But we should be able to look at it and say, okay, does this feel right as the graph? Does it look like I've shifted it down 7? Yes, that feels good. The flip feels good. I've gone to the left. It seems like things have been shifted to the left. This seems to be accurate as a result. All right. The next graph, we are going to get introduced to a new number. A number that some of you may have never seen before. It is the number E. Oh, E. Right? It's on your formula sheet, I think. 2.7182. No, they used to have it on there now. Now it's just on your calculator. You should see if you can find the number E on your calculator. The next 4 digits are 1828, and it looks like it has a pattern, but it doesn't. It's just like pi. It's a weird number.
I didn't even know that.
The number E?
Yeah.
It is a powerful transcendental number just like pi. Pi is important for the ratio of the diameter to circumference, and it comes up all over the place.
I have found E.
Okay? E is the most important number, I think, in calculus, because it is the only function where calculus is all about tangent lines. First of all, let's draw it. So if we draw e to the x, you would have 0, 1, and now you would have 1, e. Should ask your parents if they remember the show Sesame Street when they were growing up. It was like the only kids show that existed. One of the few. And on Sesame Street, they would often start by saying, today's program has been brought to you by the number 3 and the letter S. They'd always pick one number and one letter, and then they would do a bunch of things using S during that episode and a bunch of things. I was just like, Wouldn't it mess them kids up a little bit if they would start by brought to you by the number E? And just all these little kids across North America would have been confused right away.
You know the count, famously counting 1, 2, E, 3, pi.
Oh. We'd have to include all those numbers in counting. Where did E come from? Okay, so calculus is about the study of rates of change. Rates of change are measured by, like, on a straight line, a rate of change is slope. Like kilometers per hour ends up being in 1 hour, you go 100 kilometers, that's your rise over run, becomes your slope. So calculus is study of rates of change. Instantaneous rates of change are measured by, at a given point, drawing a tangent line. So at that given point, that's my tangent line. And then if we figure out the slope, on the graph of e to the x, the slope at 0, 1 happens to be 1. If we draw a tangent line at 1, e, it just so happens that the slope of that line happens to be e. If you choose another point, like for example, later on we'd have 2, e squared, it just so happens that the slope of this line happens to be e squared. And it's the only number that works out perfectly every single time. No matter which point you pick on this graph, the slope of the tangent is always equal to the y-coordinate. No other value has that property. And that makes it extra useful for doing a bunch of stuff in calculus. Interesting thing, now I'll get here. The slope of all the tangents is equal to the y value. So in calculus, we find derivatives as the equation of all the slopes. The derivative of this one is just exactly the same. And because it doesn't change, it causes your brain to do all sorts of weird, troublesome stuff. Anyway, so if you were asked to graph y equals 3e to the x minus 2 minus 1, you would start, same thing, list the common points that you have from above. You're going to multiply your y values by 3. Again, if I took out my highlighter, I would highlight the e and highlight the x. Those things aren't affecting my transformations. I think this is kind of fun. If you multiply y by 3, then your y value of e becomes 3. 3. You have to say it just right in English to not confuse it with 3. This is 3. And then once you go 1 down, you'd have 3 minus 1. And you have to estimate about where that is. 3 times 2.7 is about 8.1. This y-coordinate is at approximately 7.1-ish. And you could do graphs with e. I mean, I could give you an exponential graph where the base was pi, and it wouldn't be any harder, just as another weird number. Okay, questions for practice on this one are 10 and 13.